Hello and welcome back to my channel. Today we'll be talking about dynamics, which is the next part of this course. And basically, dynamics in kinematics we dealt with how things move, but in dynamics we're going to study the causes of things moving. So dynamics is the study of the causes of motion. So what we're going to focus on is, what is a force? Well, you may have heard what about forces before, but a force is anything that's any push or pull is a force. And the units that we're going to be using for this unit about forces, because dynamics is, we're actually going to be focusing on forces, right? Any push or pull that goes on in the real world. Anytime you pull on maybe a door handle, that's dynamics, or that's you're applying force to the door. Anytime you may kick a soccer ball, you're applying force to the soccer ball, and that's the study of dynamics. So when we're looking at any push or pull and what units we're going to use for this, well, the units we're going to focus on for this unit is going to be newtons. And how do we get newtons, and what is a newton? Well, a newton is equal to 1 kilogram times a meter per second squared. So anytime we multiply a kilogram by a meter per second squared, we're going to get a force. And that force is what we're going to technically be using. So there's a few key concepts in this unit that we're going to focus on. One of them is actually called a free body diagram. A free body diagram is something that we use all throughout this unit, and it's something that you should really get comfortable with to be successful. So in the next part, we're going to look at what free body diagrams are. Then we're going to continue talking about forces, how they apply, and what maybe different types of forces are, what the formula is for basic forces, and what net forces are. So I'll see you then. Hello and welcome back to my channel. In this video, we're going to be moving on to the next unit in this course, which is dynamics. So what is dynamics and how do we use it? Well, dynamics is basically the study of what causes motion. So dynamics, we're studying the causes of motion. And what we're really going to be talking about is forces. What are forces? Well, forces is anytime we push or pull on an object. Any push or pull is a force. So before we jump into what forces really are and how we can apply them in different types of questions, first we need to talk about Sir Isaac Newton. Basically, we have to talk about Newton's 3 laws. So Newton's first law, that is all prevalent all throughout forces, is that if an object is at rest, an object will remain at rest or move at a constant velocity unless acted upon by an unbalanced external force. So you can write that down. An object will remain at rest or move at a constant velocity unless acted upon by an unbalanced force, external. We can write Newton's first. So that basically means the key concept here is that, for an example, A soccer ball stays still unless someone kicks on it. So that means like a soccer ball, if we have a soccer ball down here, it won't move unless someone applies an external force of maybe kicking the ball, and then the ball will go like this. Or a car is moving at a constant speed. Like if we have a car on a highway and it's moving down, it's going to move at a constant speed of maybe 50 kilometers an hour, unless maybe the person hits the pedal and they start moving faster, so they have an external force, or maybe they hit the brakes and slow down. So that is in total what Newton's first law entails. So let's look at Newton's second law. Well, Newton's second law basically states the acceleration of an object is directly proportional to the net force acting on the object and is inversely proportional to its mass. So what does that mean? Well, let's write it down first so we can fully digest what it means. So the acceleration of an object is directly proportional to the net force acting on it. So, for example, let's say you're pushing a light box versus when you're pushing a heavy box. You can maybe apply the same force on the boxes, but the acceleration of them will be different. So if you have a box here and maybe it's only 3 kilograms and you're pushing on it like so, you're pushing on the box and the box is maybe moving at 3 kilograms, 3 meters per second. Now let's say you have another box, but it's 10 kilograms, and you start to push on it. Now when you're pushing on the box, because it's heavier, you may be pushing with the same amount. Maybe you're pushing with, the same amount here that you're pushing here, but the box will move at a slower rate, maybe at 1 meter per second. So basically what Newton stated was that if the acceleration is going to be proportional to the net force on a box. So the net force is basically all the forces added up, right? So if we have, you may ask like, what is net force? Well, net force is all forces added up. We'll go more into that later down when I start to explain what forces are, but that's all you need to know, that net force is all forces added up. And when Newton stated the acceleration of an object is directly proportional to the net force acting on an object, he means that the acceleration goes with the net force. So some key points to remember are acceleration increases with more force. So more force means more acceleration. And acceleration and vice versa. It's going to decrease with less force. So one formula that we can put down here for this law is going to be force, net force. You want to put a vector because usually we have direction with when we're dealing with forces. But later on we'll talk about inputting direction, and sometimes we might not need to use direction if we interpret it. But for this case, we're going to put net force. So force net is equal to mass times acceleration. And next we'll talk about more about the units, what this force means, what this A means, how they're all proportional. But that's just what Newton's law is right now. His second law is that acceleration of an object is directly proportional to the net force acting on the object. Newton's final and third law on this one is, let's write Newton's third law. Newton's third law states that for every action, there's an equal and opposite reaction. So every action has an equal equal and opposite reaction. What does that mean? Well, that basically means that, for example, if you were to punch the wall, you may wonder why your hand hurts. Well, your hand hurts because you're punching the wall and you're applying a force, but the force that you apply into the wall, you're getting the same force back into your hand, because forces don't occur without like the same opposite reaction. They come in pairs. Another example would be a rocket pushes gas downward, and the gas pushes the rocket upwards. Just like how you push down on the ground, you get another force upwards. Or how when you jump, your feet push the ground and the ground pushes you up. So all these are examples of Newton's third law. The key concept about this is that forces always come in pairs. So that's something to really keep in mind for this unit, that forces, whenever you're working with Newton's third law, you will always have forces in pairs. You'll never really have just maybe an applied force. You'll always have forces that come in pairs, especially with Newton's third law. Especially every action has a reaction. So make sure that you don't ever have an odd number of forces. That's really like the bottom line of what we're really talking about here for forces. But now let's talk about what forces are a little more in depth, and what the units are and how they really relate. So let's talk about what forces are. What forces are. So when you talk about what forces are, forces basically means it's the study of, it's any push or pull is a force, right? We talked about before how dynamics is the study of causes of motion. So the forces are push or pull. Anytime you push on something, that's a force. Anytime you pull on something, that's a force. Anytime you maybe kick something, that's a force. Anything like that. There's forces all around us. So let's talk about what the unit for forces are and how they're really used. So let's talk about what the units for forces are. So force, there's a vector because we usually have direction when we're putting force, right? So the units for forces is typically newtons. Newtons, and how do we get a newton? What is a newton? Well, a newton is basically the unit for forces. So label here. Unit. Newton is equal to kilogram times meter per second squared. That's what a newton is. And if we're talking about in specific what forces are, or not what forces are, what the symbol for forces is. So how do we say the force of something? Well, the symbol for forces symbol is basically just F with a vector sign. So from here, let's talk about what everyday forces you may encounter. So some forces that you're going to encounter throughout your life is the first one. So let's talk about forces you encounter. Some forces you encounter is first an applied force. What is an applied force? Well, if you have maybe a box here and you're pushing the box this way. If you're pushing the box this way, you're applying a force this way. So you have a force applied that way. Anytime you push something, you pull something, you're applying a force. Anytime you apply a force to something, that you have a type of force. The next type of force we have is tension. What is tension? Well, tension, we can really look at it through Newton's three laws. Tension really falls under Newton's third law of action-reaction pairs. So action-reaction pairs, the reason it falls throughout that, remember how we talked about how all forces come in pairs? So let's say if you have a box hanging from a ceiling, right? And there's going to be tension. If you look at this rope, there's tension here, right? You've heard of tension before. There's tension there. That's why the box isn't falling straight on the ground, right? That's why it's not down here. So there's a force of tension right there. But what does that mean? Well, what it really means is that this box is putting a force on the ceiling, right? So it has a force up here, and the ceiling is doing a reverse force down here. So if we're looking at this, we know that the box, if we draw it here, we know that the box has a force of the force of the box. So force of the box on the ceiling. So we can write force of B on C. We put B for box, we put C for ceiling. It really doesn't matter how or whatever you word it as, but that's basically just to keep it simple. You want to make sure you put variables because it helps you organize your work. So we have the force of the box on the ceiling, and then we also know that there's going to be another force coming down. Why? Because of Newton's third law stating that there's no opposite forces, or there's no odd number of forces. Forces always come in pairs. So if there's a force of the box on the ceiling, there's going to be a force of the ceiling on the box. So that's something you have to keep in mind when we're working with forces. Forces always come in pairs, and that tension is a type of force that you're going to deal with throughout this curriculum. So we have force applied, force of tension. The next type of force we're going to have is normal force. What is normal force? Well, normal force is the opposite of the force of gravity. So we know that gravity is always pushing us down at all times. So if we're sitting down on a chair, we know that the force of gravity is constantly pushing us down, right? We have gravity. It's pushing us down. But what's the force that's keeping us up? Well, the force that's keeping us up is the force normal, or Fn. That's the symbol for force normal. Force normal, we can use the symbol Fn. So that's what force normal is. Force normal is a force that opposes the force of gravity. We'll talk about all the symbols for all these forces after we're done explaining what the forces are. So remember, the force normal is a force that opposes gravity. Because again, forces come in pairs. That's really the bottom line. Forces come in pairs, and there's no odd number of forces when we're dealing with dynamics. The next force that you're going to deal with is the force of friction. For some of your questions right now, your friction may be negligible, so you don't have to account for friction. But what is friction? Well, friction is, to simply put, let's say if you were walking on a skating ring, right? Why is it that you are more prone to slipping compared to when you're walking just on the sidewalk? Well, the reason you're more prone to slipping on a skating ring is because there's no friction there. Friction is like what prevents, it's the opposite. Friction isn't the reactionary force because friction is just always there. Friction is constantly existing. But friction is what stops us from falling when we're in a skating ring. But it keeps us from falling also when we're on the sidewalk. But there's less friction in the skating ring, which is why you may fall or are more likely to fall in a skating ring. But the key concept here about friction is the force that, let's say if you had a car, why is your car able to stay on the road? It has a force applied. We have a force applied going this way, right? But we have a force of friction keeping the tires on the road. So you also have a force of friction opposing our force applied. Again, it goes back to Newton's third law, talking about action and reaction pairs. So again, force of friction is often a reaction pair with the force applied. That's really the words I was looking for. And the last force that we have is the force of gravity. So what is the force of gravity? Well, the force of gravity we all are really familiar with. The force of gravity is basically just a force that the Earth has at all times. This is the Earth. The Earth always has a force of gravity towards the equator. So that's a force that's on every object. You'll always encounter the force of gravity. It's what keeps us on the ground and what stops us from floating away. So what are the symbols for these? Well, for force applied, write symbols. For force applied, the symbol is typically F with the subscript A. You want to make sure to just put your vector signs. With force normal, your force normal is typically just Fn. For force of gravity, you typically have Fg. Force, when you're talking about force of friction, you have F. So, and when you're talking about force of tension, you don't want to really label your tension just T. Like if we had the box here again, you don't want to label this tension just tension. You want to label it the actionary and reactionary forces. So you want to write force of 2 on 1 and force of 1 on 2. So if this was 1, this object up here would be 2. So write force of 2 of this one on this, and force of 1 of this one on this. You want to make sure all those are clear in your given. So make sure we have a comprehensive structure for our work. Next part, we're going to talk about free body diagrams and how they apply and are really important for this unit. So what free body diagrams basically are essentially, free body diagrams are what physicists use to illustrate all the forces acting on an object. This means the force of gravity, force normal, force applied, force of friction. Free body diagrams help us see all of those. Why do we use a free body diagram? Well, if we don't have a free body diagram, and let's say we draw this car, we want to look at all the forces that are acting on this car. The force is moving, the car is moving that way, so that means there's a force of friction here. There's all these different things that are acting on the car. So we want to really just keep it simple and not have to draw complex drawings, because that's really going to waste time, especially if we're working on a test. We want to just keep it simple. So we can just draw a simple box like this, put an M in the middle because we're talking about mass, and we can draw our forces. Make sure, the really important part about free body diagrams is that we only use them to illustrate forces. There's no acceleration or velocity shown on free body diagrams. The only thing that's shown is the forces on it. So if we have this object right here for this car, we're illustrating this car, and it's moving this way. So it has a force applied that way. But the road, the pavement, is opposing the force applied and resulting in a force of friction that way, backwards. And we always know that there's a force of gravity that's pulling an object down, but there's always also a force normal keeping an object up. So now we've basically drawn a full body diagram with all our forces to really show everything that we need to show. So that's what really free body diagrams are used for. It's to really show all the forces on an object, and we have to be really proficient in drawing our free body diagrams, because then if we have our free body diagrams, we can usually solve for different variables in here. For example, it's also important to note with free body diagrams, let's say the acceleration is equal to 0, right? And if we look back to Newton's first law, if there's no force on an object, that means all the forces are balanced, right? If there's no force on an object, everything's balanced and it's not moving. So if there's no forces on maybe this car is standing still, that means our force applied is equal to our force of friction. So if we ever want to find out the force of friction, we know that's going to be the same as our force applied. So that's why it's important to really look at the question and try to use Newton's different laws to try to figure out what we have. And free body diagrams are a great way to really look at what we have and try to put the pieces together. Okay, in this part of the video, we're going to talk about net force. We talked about it previously earlier when we were talking about Newton's second law and how the mass times acceleration is equal to the net force. But what is net force? Net force basically means it's the total force, which basically means it's the sum of all the forces acting on an object, right? So our net force is really the sum of all the forces that are acting on an object. How is this useful for us? Well, we really want to make sure, well, first of all, the symbol for net force is always just F vector, force, so net. So if we have maybe a sum of forces, if we have force net, this is going to be equal to F1 plus F2 plus F3, and so on and so forth. We want to make sure that our force is the total and sum of all the forces. So if we have a free body diagram here, and maybe we have a force applied here, we have a force of normal, force of friction here. If we want to find out the net force, we have to add the force of friction with the force applied to get the net force. That's a key concept about net forces, because oftentimes when we're working in a question, we're often actually going to be looking for the net force, really. So we really want to make sure we know how we're working with net forces and we're able to determine what the net force is. So now we're just going to look at a practice problem involving forces and net forces, and we're just going to try to use this practice problem, and hopefully you can use this as a reference to when you're doing your own practice problems to practice all these. Make sure to let this digest, because this can be a lot, and make sure you thoroughly understand all of Newton's laws. But let's begin. So remember, we always want to start with our graphs method. So because we have two directions here, again, we have up and we have down. If right now we're only working in up and down, maybe the next question may involve up, down, left, right. So we'll have two dimensions, similar to how we have kinematics in two dimensions. Here we have up and down only, so we should only just set one of them as positive. So we'll set up as positive is equal to positive. So the floor exerts a normal force of 36 newtons up. So if the floor is exerting a force of 36 newtons up, we can assume, well, what does that really mean? Let's try to think about it a little bit. So we have our full body diagram. We have a mass here, right? And the floor is exerting a force that way, right? So if it's exerting a force up that way, it probably means that it's the force normal, because the force normal always opposes the force of gravity, right? So we can write Fn is equal to 36 newtons. You may actually not need, oh, pardon me, no. Make sure to put a vector sign on this, because it does have direction being up. So the force of gravity on the chair, then it says the force of gravity on the chair is 36 newtons down. So it already just tells us what the force is. So it tells us Fg, we have a force of normal and force of gravity. So we put Fg is equal to 36 newtons, but down. And because it's down, it's going to be negative. Draw a full body diagram of the chair and use the full body diagram to determine the net force. So we're required to find is force net. And we already drew a full body diagram to begin with. It's always important to draw your full body diagram in your analysis. Try to put what you have down in the given, and if you can't understand what you have in the given, sometimes drawing a full body diagram can help you just piece together what you're maybe missing. So we have all our forces here on this object. There's no other force. It doesn't say there's a force applied or a force of friction. It just says a stationary chair. Maybe if you're a little intuitive, you'll know what's actually already coming by the wording of stationary and how it relates to Newton's laws, but we can calculate it too. So we put force net, you have to put net down here, you just put force vector, is equal to Fn plus Fg. Remember, we always want to add up all our forces. So we're going to add up the force of normal with the force of gravity. We're going to add up all our forces because we want the net force, so it's the sum of all forces. Now we can just go straight into our solution, and we can go force net is equal to force of normal, which is 36 newtons, plus negative 36 newtons. and that means force net is just equal to 0. And if you were paying attention previously, it says stationary chair. If a stationary chair, if you think back to Newton's first law, an object will have all forces balanced unless there's an external force acting on it. So all these forces, our G is just equal to our Fn because there's no force of it moving, right? It's stationary, so its acceleration is 0, which means that the force of gravity will be equal to the force normal. That's something we can pay attention to, but that basically just concludes this question and this video. In the next video, I hope to cover more of dynamics, and we'll be starting to focus on dynamics of different directions. So we're going to be using force of friction, force applied, but with moving objects, and we're going to be using force of gravity and all these things. So it's important to practice these fundamental things and to really understand Newton's laws to be successful in the next part of dynamics. I hope you enjoyed the video, and I'll see you in the next one. Remember, physics rocks.